Read the question carefully. So we want to have a box with a square base. So the base is a square, means length and width are the same. And open top, there is no material on the top. And a volume of 10,976 cubic inches. So we want to construct a box like that. Now the question is find the dimensions, that means length, width and height of the box that will minimize the amount of material used. Okay, so amount of material that goes on sides, bottom, front and back, right and left. So we want to minimize that amount. So first we need to assign the variables. In this case, dimensions means, let's say length is x, and width, don't go for y because it's a square base. It's given a square base. That means length and width are same, so this is also x. Now height, we have no choice, so use different letter y. So let the dimensions be x, that's the length. Width is also x, and y. Or length is x, width also x, and height is y. Okay, and open top means there is nothing here on the top. This part is open top. And a volume of 10,976, that's the constraint. So we want to have the volume of this box exactly 10,976. Okay, so let me write down the constraint here. Volume is this. So how do we find the volume of a box? That's the length times width times height. So x times y. So x times y, that's the volume, is exactly 10,976 cubic inches, which is x square y equals 10,976. Let's solve for one variable. Solving for y is easier. So y equals 10,976 x times x square here. So let's say this is equation 1. So later when we find the value of x, then we can find the corresponding y from this formula. Okay, the next thing is we need to find the objective function. So that's what we want to maximize or minimize. In this case, we want to minimize the amount of material. So the material, when we construct a box, the material used is on the bottom, and there is no top, by the way, and there are 4 sides. Right side here, left, okay, I meant left here, same thing, right and left, and front and back, they are also same. Look at the front. Okay, I'm just getting front here. The front, this is x. I mean, we want to find the area of each side. The front, this is x, and the height is y. So the area is x times y. So that's the front, and back will be the same, another xy. And how about the right side? Right side is here. I mean, this is x, and the height is y. So x times y is area of right side. Okay, and left side is same, so xy, another xy. So in fact we have front, back, xy, 2xy, right, left, another 2xy, so 4xy. So the material goes on 4xy, that's the area of front, back, left, right, plus, now the bottom is a square, so x times x squared. So this is where we use the material, 4 sides plus the bottom. Bottom is a square base, so x times x, and that's what we want to minimize. And let's say this is the function f equals. Now we need to write this function in terms of one variable, and that will be done using the constant. So let's plug in y equals 10,976 over x squared. So that is 4x times y is 10,976 over x squared. Okay, plus, and we got x squared here. Let's simplify. Oh, x from top and bottom we can cancel 1. Then we are supposed to multiply, but let's not multiply, just leave 4 times 10 9 7 6 all over x plus x squared. Okay, now we want to find the derivative of this function. You can multiply 4 times this, whatever that number. We have to simplify later, so we don't have to worry about this. Now let's find the derivative of this function. So obviously this number times 1 over x, so this number survives and we have 1 over x, and you've seen this several times. Derivative of 1 over x, you can write x raised to -1 and use the power rule or use the quotient rule. It's gonna be -1 over x squared. Okay, so the derivative, if we have some constant on the top, some number, okay, that number is here, just constant over that x squared. So in this case, so the derivative is this constant, whatever that, 4 times 10 9 76 over x squared with negative sign. Okay, that's the derivative, plus derivative of x squared is 2x. So we have the derivative. Now we set the derivative 0 to find the critical numbers, because the maximum or minimum always happens at the critical numbers. Okay, so we set derivative 0. Okay, that means we are setting this equals 0. So -4 times whatever that number, 976 over x squared plus 2x equals 0. Now let's solve for x. So we got a fraction. Let's move 2x to the other side. So -4 times 10 976 over x squared equals, move that over, subtract 2x from both sides. So we get this, and negatives can be cancelled from both sides because we can multiply both sides by -1. We can think this is over 1, so cross multiply. Okay, then this is 2x times x squared, we get 2x cubed, 2x cubed equals, negatives gone, 4 times 10 976. We are trying to isolate x, divide by 2. So divide by 2 means then 2 divides 4 twice. So this is 2 times 10 976. Now we need to multiply, and cube means next we need to take the cube root. So x equals, cube root is same as raised to 1/3. So 2 times, you can multiply using your calculator, 10 976, multiply and take the cube root using your calculator. Use your calculator, it comes out to be 28. So x equals 28. If we go back, in fact that's our answer, because x equals 28, that will be minimize the amount of material used. But we need to verify why x equals 28 minimizes the objective function. So to check that, we need to find second derivative. To check x equals 25 minimizes the objective function, which is the amount of fencing. We need to find second derivative. Let's find second derivative. So we have first derivative here. Let's find derivative of this one more time. Okay, so when we find derivative of this, plus 2x, that's plus 2, derivative of 2x is 2. So first part, you have a number over x squared and there is negative sign, so just work. And so when you find the derivative of this, you can just leave this as a constant, 2 times 10 976 and 1 over x squared, or if you move up, that's x raised to -2. And when you find the derivative of x raised to -2, that is -2x, -2 minus 1, -3, so -2 over x cubed. That's gonna happen. Okay, and I wrote 2 over x cubed, that negative, and we have negative in the front, they'll cancel. Okay, or you can use the quotient rule if you like. In any case, this is the derivative of our first derivative, so this is the second derivative, and we want to evaluate this second derivative at 28. Okay, so at x equals 28, the second derivative will be positive, because if you plug in 28 cube, everything is positive divided by positive, so this is a positive number, plus 2 will be positive, so I don't have to even evaluate positive number. So this will be a positive number that bigger than 0, and when second derivative is 0 at this point, so nearby we'll get concave up graph. Okay, nearby 28. Okay, that means the minimum. So from the second derivative test, when a critical number, at critical number, if the second derivative is positive, we get minimum. So x equals 28 minimizes the function. So we go up and find all the dimensions. Look at here, we are finding the dimensions x, x, y, length, width and height. So that's 28 is length, width is also 28, and now we find y, the height from here. Use your calculator. 10,976 divided by 28 square, that will be the height y. So let me write that over here. So plugging in 28 square here, we get 14. So 28, 28, 14. So let's go all the way down and write down the final answer. Thus the dimensions are 28 feet by 28 by 14, I think inches. So okay, final.